wait for... All right. While we have this handsome young man on the screen here, I'll start off with a thank you and with an apology. So I just want to say thank you to all the folks involved putting this conference together. This is my first KXCon. I don't work on Wall Street, but it's been extremely lovely to meet all the folks that do work on Wall Street, companies like Citadel, Millennium, etc., Jump. And it's been amazing to meet all the folks at KX. I know Stephen Taylor, I'll mention that a little bit later. But yeah, this conference has been absolutely amazing. And anyways, a round of applause for folks, involved in setting this up. That's the thank you. My apology is that I'm going to have to apologize. Erin's presentation yesterday, where she brought her Oprah level of energy, made me a little bit concerned, because I think I'm pretty energetic, but I was watching that and I was like, Jesus, this is going to be quite boring compared to her presentation. So I apologize if I don't bring that Erin level of energy. So this talk's going to be a lot different than a lot of the talks that have been going on so far. It's going to be not as technical. Absolutely loved Pierre's talk yesterday. So far, the highlight of the conference for me so far. But we're gonna make a couple jokes off the bat. So probably most of you know Connor at this point, which is confusing because I am also Connor, and there's actually 2 other Connors that I've met at this conference. I don't know what's going on in KX. Like I might be working for KX soon, just not because I'm talented, but my name is Connor, and so. I was curious how many Connors. I don't know if these Connors are all actively employed by KX, but yeah, there's 8 of them. And anyways, all of the Connors that I've met, is it 3, 4 including me here, are the other folks? So 4 Connors here. Yeah, all the Connors I've met are lovely. Everyone else who's not named Connor has also been lovely. But of the Connors, how do I differentiate myself? And it's great running culture at KX from what I've heard. Ashok, the CEO, is a marathoner. If you check out his Twitter, that's one in the bio. I'm also a runner, and I'm glad to say that I am the fastest Connor at this conference. So I have been busy running while I've been here, so there's a website called City Strides. So for any of the runners in the audience you don't know about this website, it basically amalgamates all the runs if you sync your runs on Strava. And so as you can see, I am now the number 2 city strider in Montauk. I've run 17%, if you can make out that percentage, of the roads in Montauk. So it basically ranks you as you complete the different roads in whatever city you're in. So this is, I'm from Toronto, Canada, if this works. So this is basically, I've been busy. I talked to someone once and they said, Connor, you don't have hobbies, you have passions/obsessions. Anyway, so citystrides.com if you want to check that out. All right, that out of the way. My talk today is called Algorithms in Q. As I mentioned before, my name's Connor Hoekstra. Online, my alias is Code Report, so if you can't find me through Connor, you can look that up. And we're going to do a little about me, just to introduce myself. So I have been in the industry for 10 years now. I actually started my career as an actuary before switching to the tech industry. After 4 or 5 years of working at Moody's, I was working on an insurance product called Axis, if there's any actuaries in the room that used to work. Yeah, if you know Axis, I used to work on stochastic calculations, coding in C++. Switched to Amazon, went down to Silicon Valley for a year, and then ended up switching to NVIDIA, where I've been for the last 3.5 years, coming up on 4 years this summer. The first 2 years, or I guess 2.5 years at NVIDIA, I worked on a library called Rapids. So this was not initially in my slide deck, but I've heard pandas mentioned 2 or 3 different times yesterday. So Rapids basically focuses on GPU accelerating a bunch of Python libraries. So the one that I worked on was called cuDF. The DF is for data frame. So if you happen to be using pandas and you find it too slow, you may or may not be able to go check out some of the libraries there. But that's what I did for the first 2.5 years. I was basically working on the CUDA C++ backend to the Python interface. So check out Rapids if you want, not what this talk is about. Throughout my career, I've been a C++ developer primarily. I'm not a KDB developer at the moment. But I kind of consider myself a polyglot at this point because I know, 10 languages, only 2 or 3 really well. But C++ has basically been my driver language for the entirety of my career. Back when I was at Amazon, I joined the ISO International Standards Organization for developing the language and joined the Canadian National Body at some point. So for a year and a half before COVID hit, I was going to committee meetings working on evolving the language. So if you have any questions or want to chat about C++, have some expertise in that area. But when I was at Amazon, they started this study group to learn about functional programming. And at that point, I basically knew Python, Java, and C++. And had dabbled in a bit of Go and Perl, but Haskell was completely different for me, and it absolutely blew my mind. It changed the way that I thought about solving problems by a factor of 10. And so at that time, Haskell was my favorite programming language. And then I discovered APL. There's a whole longer story of how I ended up sort of falling down into the array language rabbit hole. My little sister works at well, she's not very little anymore, but she's grown up, and she works at a hedge fund in Vancouver, Canada. And that was actually the first time I heard about Q, because their hedge fund uses KDB Plus and Q. And I was like, that's odd. I'm a software developer, and I've never heard of this language. And I went and Wikipedia'd it and said it was a derivative of the APL language. And basically, in December of 2019, I started really taking some serious time to look at these languages and have not looked back and have parlayed my career into researching that at NVIDIA. So now I work on the research team at NVIDIA, working on basically investigating new programming models, and my hopefully goal in the future is to do something array language related. But that's a discussion for another day. So if you don't recognize all of these symbols, I assume most of you know APL and J, but I've talked to a few folks that did not know about this new symbol, and that's BQN. BQN is the newest array language on the block. It doesn't really compete with Q. It's more similar to APL. And BQN, if maybe a couple of you have put it together, it was originally supposed to be APL plus 1, shifting each character by 1. But if you try and do that, you'd end up with BQM. And so they actually messed that up, but they created a backronym that was big question notation. And so they've stuck with it, and now the joke is that BQN is APL plus Fibonacci. I appreciate that half the room, or if not all the room, got that joke. I was a little concerned. But anyway, so, and here's my one request. You might be noticing that there's no logo for KDB Plus or Q, and that's because there is no logo. You can technically use the KX logo. I was at a KX Systems meetup before COVID in Toronto, and I talked to a few dev advocates there, and I made that request, because the APL logo actually was only created in the last couple years, and it also came from me being I need logos to put on my presentation. So anyways, if a KDB or a KX wants to create a logo for KDB Plus and Q, I would love that. That'd be great. Anyways, back to the about me. We'll get through this. I also have a YouTube channel that started 5 years ago. And I'm also on Twitter, Code Report for both of those. I have a meetup where we go through different textbooks. So the logos up there, structure interpretation for computer programs, category theory for programmers, etc. And I also have 3 podcasts, which is probably what some of you know me from. So the main one is Arraycast. So Arraycast is a podcast that focuses on the array languages. I'm the host. There's typically 4 panelists. Stephen Taylor from KX represents Q. Adam Brzezinski from Dialog APL represents APL. Bob Terrio represents J. And we recently added Marshall Lochbaum, who represents BQN. We have interviewed a ton of folks, many of whom you will know. Ashok was one of our guests. That was an awesome conversation. Nick was also on as, I don't know where Nick is. Nick was on both as a guest and I think as a guest sort of panelist a few times. And Attila, I'm not sure if Attila's in the crowd. But Attila was a guest as well. I think that's all the guests that are currently here. We're going to get Pierre and Oleg on, even though they have not agreed to come on the podcast. But I can't remember if it was I talked to John, and John just said, talk to Ashok, and he'll force them to go on. Anyways, there's been other folks, Eric Iverson, the son of Ken, obviously. He's been on the podcast. Stephen Apter, Joel Kaplan, 1010 Data. I have a ton of fun doing it, and if podcasts are your thing, you might want to check that out. Other podcasts is with a fellow NVIDIAN who's based out of New York, and we just chat about algorithms and stuff. And I also have, this is less relevant to what I'm talking about today, but a podcast called Run for the Fun of It about running that was started recently with one of my best friends, and he's a varsity track athlete. And on top of that, 318 videos on YouTube, 31 talks given at different conferences. Links to all of this stuff can be found on a GitHub repo called Content, and that's all I'm going to say about myself. Actually, one final note. So this isn't about me, I promise. there's a GitHub page called Array Language Companies. So I don't want to call Q a niche language, but let's be honest, it's a niche language. And different programming languages like Haskell, Elixir, they create these lists which basically document the companies out there that you can go find jobs at. So there is one that exists for array languages, APLJ, KDB+, Q, etc. So feel free to go to this link afterwards. If you work for a company, check if you're there. If you're not, it can be a great recruiting tool, / it also just brings more awareness, because like one of the top questions you get when you say, oh, I love APL or Q, it's like, do companies even use that? And I think for Q, like the answer is definitely yes. There's a conference entirely dedicated to the language and companies that are using it. So, on to the content of my talk 10 minutes in. This is a part of sort of the abstract of my talk. I said viewers can expect to learn the utility and importance of fundamental built-ins in the language, such as scans, reductions, where, cut, prior, and more. So what we're going to do in this talk is hopefully highlight using 3 very simple problems compared to some of the talks that we've seen. This is definitely not as involved as the stable marriage problem in Nick's talk. These are a lot simpler. Hopefully this will be interactive. You guys can shout out, what's the next function we need? And then we're going to work through these and just show how you can code at the speed of thought. One of the things I love about array languages is that it completely gets rid of the unnecessary. And you just are able to solve the problem with the primitives that I want. When I'm in C++, love the language sometimes, hate the language most of the time, and that's because I need to spell so much. It's a great language, very fast, industry uses it, but I miss so much that I get when I'm programming in array languages. So the problems can all be found at top 10. There's actually 10 problems there. We're only going to be solving 3 of them. This is a full list of all the Q solutions, at least my versions of them. We're not going to go through this because we don't have time. But if you're interested, there are other problems that I like. I consider them sort of like intellectual gym exercises of, while I'm running, I like to think about these things. The 3 problems that we're going to solve are Sushi for 2, Max Gap, and Skyline. We're going to do them in reverse order because it's sort of easiest to hardest. And hopefully the first 2 won't take that much time. And then the last one we'll spend hopefully 10 minutes or so on. And hopefully there'll be 5 minutes for questions at the end. So the first problem is Skyline. And this was actually a problem that was presented in the most recent virtual Dialogue Appleseeds conference. So Dialogue puts on a couple different conferences. One of them is geared at beginners. And so it's supposed to get people that are array language curious, potentially interested in actually using the language. So this is essentially the problem. You're given a vector of integers that represents a skyline, and you're asked if you're standing to the left, how many unique buildings can you see? So obviously the third building that has a height of 2, if you're standing on the left, you can't see it because it's blocked by the buildings of height 5. So pretty straightforward. The solution to this, if that's not drawn to scale, this is drawn to scale. Note, I was using squares before, but Windows 10 doesn't support the emoji for green square, so I had to use hearts, if you're wondering. But the simple solution to this is basically to fill in the gaps that you see, which sort of the red hearts represent. And if you do that, you can then basically remove the duplicate heights, and you're going to be left with the number of buildings that you can see. So it's a very simple problem, very straightforward, and also extremely simple to solve in a language like Q. So this is our list of values. We're going to start off by defining a function. This is the identity function currently. And does anybody know the first function we need?
Maxes.
Yes. So an alternative spelling of that is max scan. So scan is a generic function that takes any binary operation. The pipe is the max binary operation in Q. But very nicely in Q, you have actual names for scans. So I think Q probably is the only language that I know that has spellings for explicit scans with sort of hard-coded binary operations. Every other functional language, you don't get that. And amazing thing is that I love the symmetry between reductions and scans. Max and maxes is a reduction and a scan. The one thing that upsets me about Q is they called the reduction over, and that also has no symmetry with scan. I would think it would have been really nice if they had called the reduction fold and the scan folds, because it would keep that sort of symmetry. But hey, that's just a small complaint. Anybody know the next function that we need in order to remove the duplicates? Distinct. Yes. And we are 67% of the way there. And after that, we just are making a call to our length function, which is count, and we're done. That's it. I don't have a Python solution or a C++ solution. I do have one later, but it just warms my heart that this is a pretty simple problem, but you have all the built-in, the primitives built into the language. Like there's nothing I have to do. And even, this is actually, in my opinion, a bit excessive. We can get rid of the parentheses and the x by just using the double colon. So we don't even need to name our variable. It's fantastic. So 1 problem done, 2 to go. And oh yeah, so this is actually the APL solution. So for for those of you that don't know anything about APL, they use absolutely beautiful Unicode symbols. And if you squint hard, it's actually very, very similar to our Q solution. It just looks entirely different. So like to an APL programmer, it actually reads identically to the Q solution. This is called tally, that's called unique, and then you have a max glyph combined with a scan. So this one says count distinct max scan, aka maxes, and the APL reader reads this tally unique max scan. It's the same thing, it's just a different spelling.
K would be mostly the same.
Yeah. We'd use ASCII characters, but yeah. We love all array languages. So this is the only APL code you'll see though. So here we, so we've covered now a scan, and we've coupled a couple more, count and distinct. So we've got reductions, where, cut, and prior to go. So hints for future solutions. The second problem is max gap. I absolutely love this problem. And it is a little bit more involved. And basically, once again, you're going to be given a rank 1 array, a vector of integers. And the question is, what is the maximum gap between 2 adjacent integers after sorting the list? So you're looking for sort of what is the furthest apart 2 numbers are after you sort. So if you walk through what the solution would be, obviously the first thing you're going to want to do is sort. Then you're going to want to basically take the difference between adjacent elements, and then you just want to identify the maximum from that list of values. So once again, a pretty straightforward problem, but we're going to see how we can solve this in Q, also very elegantly in my opinion. So we're back to our original. We've got the identity function. Anybody know the sorting function in Q? Ask. I actually did not know how to pronounce it. I would assume you say the C, even though in ascending you don't, because then you'd be saying something that's not safe for work. But ask is our sorting function. And does anybody know the next function we need? Deltas, yes. And I absolutely love deltas. I think, actually, we're not going to look at deltas. We're going to look at prior later. But deltas is an amazing function. And then last but not least, we're just going to get max using max. So is this correct? No. Exactly. So that is Andrew, right? Andrew at the back on the core KX team. I was going to ask, what's the problem here? But I already saw it. And this is actually, I had a big discussion with Phineas on the drive out here. I think that prior, potentially deltas and differ is the more useful semantics for that algorithm. But prior, in my opinion, which I assume deltas and differ is implemented in terms of, is a little bit broken in that it's the first value. So if we go back here, the problem here, so that's the point-free version. We can drop the x. The problem here is that what if you copy the first element to be the first element of your output sequence, when really, when you're doing deltas, you could implement it such you end up with 1 less element in your resulting vector. But because you want to preserve the length, they say, oh, let's just copy the first element of our input sequence to be the first element of our output sequence. But what does that mean? What happens if instead of 1, our first value is 10? Now when we do the max reduction, we're actually taking the first value, not a delta. So in my opinion, actually, deltas, or at least prior should have different semantics, but Phineas disagrees. And yes. So let's chat about this afterwards. Like Phineas and I swear, for 45 minutes in the car, he was like, "No, I don't agree." But yeah, we chat afterwards. And anyway, so yes, you have to do a 1 drop in order to have the actual correct solution, and then you put the max in front, and then we're good to go. So we are doing pretty good for time. We've got about 8 minutes to solve our last problem. So what have we done now here? We've done reductions. We've almost done prior, because deltas is like a specialization of prior. So we're left with where, cut, and then we also have to see prior in action. So our last problem is the most involved. This one is not entirely trivial. We're going to need 2 functions in order to solve this. But it is probably my favorite problem of all time that I've come across. And I'll explain why in the end. First, let's explain the problem. This one's a little bit trickier. So you're given basically a vector of integers, 1s and 2s. The 1s represent tuna, and the 2s represent pufferfish. And you are basically going to go to a restaurant that is going to have tunas and pufferfish in a line. And the statement of this problem is, you are with a friend, your friend likes pufferfish, you like tuna, and the food that you're going to eat has to all be contiguous. So you're going to take some of this fish, but it all has to be in a row. And the criteria are, it has to either be like tuna, 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 pufferfish, 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 or reversed. You can't have them back and forth. So it's going to be all one type of fish, followed by another type of fish, and each person has to get the same number. So if I get 2 pieces of fish and I'm there with Connor Toomey, he has to also get 2 pufferfish. And so the question is, what's the maximum number of fish that we can eat together with that criteria? So in this example, the maximum is going to be the last 4, because it's 2 tunas followed by 2 pufferfish. We each get 2, and we're not swapping back and forth. They have to be in that order. So just because that is a mouthful, we've got one extra example here. And based on those criteria, can anyone figure out what the answer is for this example? 3 and 3, yes. So in total, you're getting 6 fish. Each person's getting 3. So you guys are super bright. I'm going to grab this bottle of water. I gave this a version of this talk internally at NVIDIA, and we had like a 5-minute discussion on they were like, I don't understand. It might have been my fault, but or maybe you guys are just all a lot brighter. So this is the answer. 6 is definitely correct, 3 for each person. And so we're going to go through and solve this. The first thing we need to do is build a helper function that I call chunk, which is spelled right here. But we're going to work through what that does. So first things first, we're building up chunk. The first function we need is differ, and that's going to basically tell us where our adjacent elements are different. And we're going to combine this with where to get the indices of where those changes happens. And once we have this where differ x, we can use this to cut our initial vector, and then that's going to give us basically a list of lists. This is not the representation if you do it in the QREPL, but it's easy to visualize here. So basically, you end up with contiguous equal values. So this is what we need in order to basically solve the next step of the problem. Hopefully this makes sense. So now we're using chunk. Does anybody know what the next thing we might want to do is? Yes, exactly. Once again, Andrew in the back. Count each. So this is going to give us the length of each of our sort of sequences of fish. So at this point, we don't really know which is tuna, which is pufferfish, but we don't need that information now. So once we've got our count each, does anybody know the next one? This is probably the trickiest step of the problem. Andrew, crushing it in the back corner. A min prior, correct. So you basically want to take the minimum value in between adjacent lengths, because if you have 3 pufferfish and 2 tuna fish, you want to drop that extra pufferfish because we have to eat the same number of fish. So you do the min prior, and then once again, because we're using prior, we have to do a 1 drop. And actually, this is a little shout out to a website that I'll be publishing sometime later. So you type in a name of a function, and it gives you all the semantically equivalent functions in other languages. So this prior, actually, I knew about from Haskell previously. It's called adjacent difference in C++. But I was super excited when I discovered prior in Q, because it is by far the easiest way to spell this if you look at the spellings. And adjacent transform is a C++23 range adapter that was added just recently in the last year. And it has the exact semantics that I was explaining earlier. Adjacent difference does the same thing that prior does, where it copies the first value to be the first value in the output sequence. So like I said before, we also have to do the 1 drop, though, in order to get rid of the first element. And then last but not least, we are going to take a max and then multiply that 2, because you need to do that in order to get the right answer. And that, I believe, brings us sort of to the end of my presentation, except I've got two small things to say. So that's our final answer. This is the solution in C++. And this basically sums up why I love array languages so much. This is not the most elegant way to solve this. Using C++23 range adapters, you can solve this actually in like 4 or 5 lines, but that was not possible until the last 1 or 2 years, and you also have to be using C++23 in order to do that. There's so much state here. There's loops. We hate all of it. Compared to this previous solution, like this is just, the 1 drop is a little bit irritating, but everything else is exactly the primitives that I want. And yeah, so Q, just an absolutely beautiful language. And I think there's one other thing. So yeah, wrapping up, where, cut, prior, deltas and differ, you can see are next to prior because they're kind of specializations. And I think I have one kind of bonus slide. So this is nothing to do with what I presented on, but this is kind of a little bit of my research. And so if you're interested in chatting about this afterwards, this is more of just like a conversation starter for later this evening. This is a mini interpreter, more like desktop calculator that I've implemented that has like 3 different backends. One is in C++, one is in C++ using ranges, which basically fuses operations together. It's like a collection oriented. If you're familiar with Java 8 streams or Rust iterators, it's a library similar to that. And then CUDA is a bunch of custom stuff where I like wrote an IR that fuses stuff together. But basically, this just shows that like one of the properties of array languages that I find irritating is that you're constantly doing copies whenever you perform operations. You do a transform followed by like, or a scalar operation followed by a scalar operation. You're potentially creating a bunch of arrays unnecessarily if at the end of the day you're just doing some reduction. And this is basically like proof of concept that you could build some interpreter that fuses scalar operations together, and then at the end of the day, if it's doing reduction, doesn't materialize anything except for that number. It's similar to some other projects that exist out in the wild. But anyways, that's it for my presentation, and I'll say thank you, and questions if there are any. I actually don't know what my time. Am I 5 minutes under, or are we 5 minutes over? Yeah? Oh.
I was thinking the same thing.
What, this?
Well, you noticed them, you had one where they all spoke together. It was class.
Yeah. So I, on my YouTube channel and across different conferences, the #1 question I get is, how do you do that code transition? And I made a YouTube video on it, and I was telling Nick this. It's kind of sad. It's like my second most popular YouTube video of all time, and has like 150,000 views, and it's like nothing to do with what I like making videos about. But if you'd like to know, Microsoft 2019 has a transition called morph, and it's got 3 different settings. If you set it to words and you have code, it'll just figure out, where each word is going, and it's literally just a transition. I've done nothing special here. Yeah. I just thought you were using morph when I saw that. If you hired a vendor, I'm very sorry, Johnny. All right. Find me after if you want to chat about anything in my talk. Thank you.